Okay, here is the solutions to the exam 2. I'm just going through version 1. The versions are very similar, just so the questions changed around. So, for question 1, which conformation shows below represents 3-bromo 2-methylpentane when viewed through the C2C3 bond? So, let's start by drawing 3-methyl 2-bromopentane. So 1, 2, 3 bromo, 2-methyl pentane, and we're looking from this carbon to this carbon. So on the front carbon, we have 2 CH3 groups and a hydrogen, and luckily we don't have to worry about stereochemistry because this isn't a chiral center here, and neither is this, so we don't have to worry about it. So let's look for 2 CH3s and a hydrogen on the front carbon. That one's right, 2 CH3s. This is 2 CH3s and a bromo. So just from knowing the first carbon, you can get rid of that one, and you can get rid of this one, and you can get rid of this one. So we've narrowed it down to 1 and 5 are our only options that have the correct thing on the front carbon. Then on the back carbon, we have a CH2CH3 that's coming off here, CH2CH3, a bromo, and a hydrogen. So let's check and see. Structure 1 doesn't have the CH2CH3. It has a total of only 1, 2, 3. Yeah, it just has 2 methyls on, it only has 1 methyl on the back carbon. So that one's not right. So the only one that's possibly left would be answer choice 5. So let's look at that and make sure it has a CH2CH3, it has a bromine, and it has a hydrogen. So this is your right answer. So that's just kind of a test-taking technique. If you want to narrow it down based on just the front carbon, then you're already down to just 2 answer choices. You have to 50-50 shot of getting it right. Okay, next we'll look at trans 1,3-dibromocyclohexane. So if it's 1,3, one's going to be pointing up and one's going to be pointing down. 1, 2, 3. And this one would be axial. If this had a wedge, it would be equatorial. If this had a wedge, it would be axial, so this would be equatorial. So we need 1 axial and 1 equatorial. So let's see if I'm going to draw just my bromo. 1, 2, 3, something like that. I guess we can just check and see which one of these has them 1 axial, 1 equatorial on 1, 3 carbon. So these are both equatorial, so that's not right. 1, 2, 3. This has 1 axial, 1 equatorial. 1, 2, 3. 1 axial, 1 equatorial. So the right answer is D, 1 and 2. Okay. Okay, so then the next question is about constitutional isomers. So which of the following is not a constitutional isomer of the other? So I'm just going to line up next to each one. There's carbon, hydrogen, and bromines. Carbon, hydrogen, bromine, carbon, hydrogen, bromine, carbon, hydrogen, bromine, and carbon, hydrogen, bromine. So we'll start with the bromines. There's 1 of each, so those are all equivalent. Now let's look at the carbons because that's easiest. Then hydrogens. 1, 2, 3, 4, 5, 6 carbons here. 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 Okay, so it's going to come down to the hydrogens. Kind of a bummer because those are the hardest to count out, but anywhere there's an implied hydrogen, I'm just going to draw a line. So let's see, this has 1, 2, 3, 4 bonds. This has 1, 2, 3. So 1, 1, 2, 1, 2, 1, 2, 1, 2. So this has 2, 4, 6, 8, 9 hydrogens. This has 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. So both of these have C6H9. This has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This has 11. So that leaves me a question mark in my mind. I don't think that's a constitutional isomer of these two. Let's see. 1, 2, 3, 4. So 1 right there. 2, 3, 4, 5, 6, 7, 8, 9. So this has 9, and 1, 2, 3. 1, 2, 3, 4. Neither of those have any hydrogens. 4, 5, 6, 7, 8, 9. So that leaves us with a total of 9. So the only one that doesn't have 6 carbons and 9 hydrogens is answer choice C. Okay, what is the relationship between these two molecules? Well, first, I'm looking at this and noticing that this is flipped over, right? So this OH group isn't right here, it's down here. So I'm going to imagine flipping this over. So not taking a mirror image or anything, but literally taking this cyclohexane and moving it. So that means if we flipped this over, my thumb's on top pointing towards me. If I flip it over, now it's on the bottom pointing away from me. So this hydrogen or this alcohol, it starts pointing away. When you flip it over, it'll be pointing towards. And then here, this is a dash or a wedge coming towards us. And when we flip it over, it would go towards the top, pointing away from us. So let's see, 1, 2, 3, 1, 2, 3 carbons. And then down here, this is a wedge, or this is a dash going away, and when you flip it over, it should be a wedge coming towards us. Okay, so if I'm comparing these now, this looks like a mirror image, this is a mirror image, and this is a mirror image, but this last carbon isn't a mirror image anymore, right? So if this isn't a mirror image, but these two are, it's not an enantiomer, so it must be a diastereomer. So if you want me to go through the chart here, if we have isomers, these are definitely isomers. They have the same number of carbons, hydrogens, everything. They're not constitutional isomers because they're not built differently. They have the exact same arrangement and attachment. So the next option is stereoisomers. And if they were mirror images, which after we flip this one over, is easier to see that this side is a mirror image, but right here it's not. So if they were fully mirror images, it would be enantiomers. I just forgot how to spell that. But if they were, because they're not fully mirror images, the only other option is diastereomer. So I think the answer here would be answer choice B. Okay. The next one, consider the graph below, which is a plot of the relative energies of various conformations of hexane viewed through the C2-C3 bond. Okay, so I actually don't even have to draw the Newman projection to answer this question. The lowest energy conformation is going to be anti, with the biggest groups fully opposite each other, right? So I know that anything at 180, this lowest energy point, is going to be anti. And then at 0 and 360, it's going to be fully eclipsed, with the biggest groups covering each other up completely. And then the smaller groups over here. So that tells me what's going on here and here. Now, these other lower energy are anti, but they're going to be gauche. So they're still going to be staggered. I mean, not anti. They're staggered, but they're gauche because they're low energy, but they're not as low as the anti position. And these are going to be eclipsed, but the biggest groups won't be eclipsing them. So the question is asking me what's going on at 60 and 300. And so I already know these have to be staggered because these are the eclipsed positions, the higher energy. So they're not eclipsed. They have to be staggered. It can't be anti because that's what's happening at 180. They're not more stable than the conformation at 180 because that's the absolute lowest. And so the only option is either B or none of these choices. But we've already talked about how B is correct. So that they are staggered and they're going to have the biggest groups opposite of each other, or right next to each other like this. Question 6 is which of the following is a meso compound? So for which of the following is a meso compound, what you're looking for is a plane of symmetry right through the middle. So you have to have the exact same groups on both sides of this, on each of these chiral centers. But right here, this is not the same group as this. It's CH2OH and this is CH3. So 1 is not an option. So that narrows it down to 2, 3, and 4. All of these have CH3, OH, and hydrogen attached to each point. So then we want to see if there's a mirror image across. Now these CH3s are already lined up and these two are not. So there's no way that this could ever be a mirror image. Even if we rotate it, it doesn't matter. This is not going to be capable of reflecting across because this is already reflecting across and these two aren't. So if you change anything with these, this is going to change. So this can't be a meso compound. Same thing here. These alcohols are already reflecting right here across. But if you were to do anything to try to make these line up, the CH3s reflect, you'd either have to break bond and swap these out, which is not keeping the molecule the same, or these alcohols would move around. So this is also not. So now we're left only with answer choice 4. Answer choice 4 is actually tricky because there's nothing already lined up, right? There's no group already reflecting. So whenever I have a question like this, I just try to get one group to line up. So I'm just going to pick CH3 just because it's pointed upwards. So this CH3 would have to rotate down, this OH would rotate up, and this hydrogen would rotate over. So I'm going to redraw this. I'm going to do the shorthand Fisher configuration. So this top one is exactly the same. I didn't change anything, but I moved the CH3 down. I moved this OH over and this hydrogen over. So now if you draw a plane of symmetry right there, you can see that this is a meso compound and it reflects. So the right answer is answer choice D. Okay, for question 7, the rate law of nucleophiles, a nucleophilic substitution reaction of a secondary alkyl chloride with this ion. So this is actually, first you have to say, this is substitution. Is it going to be SN1 or SN2? It's secondary, so it could actually favor either way, but this is an I minus ion. So whenever I'm doing my chart, if you look at the nucleophile, if it's strong, which usually means negative, it's going to favor a 2, either an SN2 or an E2. And if it's weak, which for a nucleophile typically means neutral, then it's going to favor 1, SN1 or E1. Well, in this case, this is a strong nucleophile. I won't say anything about its basicity. It's a strong nucleophile. We already know it's going to be a substitution, so that's enough to tell me it's an SN2. So for an SN2, the rate law is K is the substrate and the nucleophile. K times the substrate and the nucleophile. So in this case, the rate would be K times RCl and I minus. They tell us secondary alkyl chloride, RCl, with a I minus ion. So that's answer choice C. And really, because they told you it's a substitution, all you have to identify is if this is a strong nucleophile, and then it will be a substitution, unless it's with a tertiary. So, okay, now what is the relationship between the following two molecules? Okay, first I'm going to check to see if these are meso compound, because then they'll be identical. But this CH3 lines up and reflects across itself, but these other two don't, which is really similar to this case right here. So that's not a meso compound. And same thing here. These alcohols are reflecting, but the other groups are not reflecting. So these are not meso compounds. So they're not identical molecules. They are isomers. They have the exact same things attached to them. So we can get rid of that. And they're attached in the exact same order. So they're not constitutional isomers. So they're either diastereomers or enantiomers. So what I'm going to do is actually see if I can't line up these CH3 groups to see if this is a mirror image or not. So if the mirror image of this molecule would have a CH3 here, a CH3 here, an OH, an H, a hydrogen, and an alcohol. Okay, so this is the mirror image of this molecule. My question is, can I get this to line up with this? If I can, it's an enantiomer. If I can't, it's a diastereomer. So this alcohol would have to go over here, the CH3 would go over here, and the hydrogen would go there. If I rotate those all that way, then I would get a CH3 here, an OH here, and a hydrogen. So far, this does look like a mirror image on the top carbon, but we have to check the bottom carbon too. The CH3 would go over one, the alcohol would go down, and the hydrogen would come over. So CH3 here, alcohol here, and the hydrogen here. Okay, so this is a match. These two look exactly the same, which means that this is the enantiomer. You just have to practice rotating those Newman projections. So the right answer should be answer choice C. Okay, for question 9, this is actually kind of a tricky one, I think. But it says, consider the following reaction. What would happen to the rate of the reaction concentrations if both the nucleophile and the substrate are doubled? So you have to decide if it's SN1 or SN2. And the reason I'm saying SN1 or SN2 and not E1 or E2 is substitution results in the swapping out of a group. So we swapped out chlorine for iodine, whereas elimination results in the formation of a double bond. And that double bond formation isn't happening. So this must be some kind of substitution reaction. And normally, if you have an I minus, then I would say, oh, that must be an SN2 reaction, except this is with a tertiary leaving group. So that's not going to favor I. Even though this is a strong nucleophile, it's not going to have a good time getting in this hindered leaving group. So actually, I would say it's going to go by SN1 in this case. So if you double the rate of the reaction of the nucleophile and the substrate, it doesn't matter for SN1 because the rate is just equal to K times the substrate. So really we just care that we doubled the substrate, so that would double the rate. Okay. For question 10, which compound is 2S3S23-butane Okay. Well, this compound 1 is different from the other 3. So first I'm just going to make sure it is 2,3-butane at all. 1, 2, 3, 4. You have 4 carbons, so it's butane, but it looks like the alcohols are on 1, 2 in this stricture 1 instead of on 2, 3 like all the rest of them. So number 1 definitely is not it. Okay, so then for the rest of them, though, it's 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So all of them are butane, and it looks like all of them have the alcohols on the right group. So, okay, which compound is 2S3S? So I'm going to start here because the hydrogen's already pointing backwards, so that makes my life easier. And it looks like all these are isomers of one another, so that's also going to make my life easier, but the alcohol would be the highest priority. Next, we have 2 carbons, and if you're comparing what the carbons are attached to, this carbon is attached to an O, a C, and an H, where this is just attached to 3 H's. So this is the next priority, and this is 3. So if we connect 1, 2, and 3, this is 2S. And then here, we have highest priority, 2 and 3. 1, 2, 3. So that would be R, except that the hydrogen's pointing towards us, not away from us. So we invert it. So this also should be S. So I'm going to probably say that 2 is the right answer. But just to make sure, I always like to work all of them, and we can do it pretty quickly because now we know that if we have this CH3OHH, in this order, CH3OHH, CH3OHH, then it's going to be S. So CH3OHH, that's the opposite. So I'm going to go ahead and do 1, 2, 3. This would be S configuration, except that the hydrogen's pointing towards us, so it's R. And then same priorities here, 1, 2, 3. This would be R configuration, except that the hydrogen's pointing towards us, so it's S. So 3 is definitely not right because both of them need to be S and 3 is an R. So we can get rid of that. Now we can look at this carbon 4, has the same priorities, 1, 2, and 3. So this is S, except the hydrogen's pointing towards us, so actually it's R, so this is SR, so that's also not right. So the only correct answer is answer choice B. Okay, the next one. Rank the following in terms of nucleophilic strength. So one of our rules of nucleophiles is if the atom is all the same, it parallels basicity. Nucleophilicity parallels basicity. So because these are all sulfur would be the attacking atom, you can do that. But you don't even have to think about that. If you just know a negative nucleophile is better than a neutral nucleophile, is better than a positive nucleophile, you can answer this question based only here on this. The most strong nucleophile is going to be negative, then neutral, then positive. So let's start by making sure either 1 or 4 is in one of the first positions. 1, 1, 5. So that one's wrong. 1 and 4. Okay, so we know that 1 being negative, and then 4 is going to be the top 2 positions. So this has 1, 4. This has 1, 2. This has 1, 2. So these are neutral ahead of a negative, so neither of these is going to be right. And that's all you need to know. Really, all you need to know is negative is better than neutral to get this question right. But if you also just looked at the last and the first one, you could see negative and then positive and eliminate anything that doesn't have positive as the least and get it down to just answer choice A and B. So C doesn't have positive as the least, D doesn't have positive as the least, E doesn't have positive as the least. So if you just know that this is going to be the least nucleophilic and one of the negative charges is going to be the most top 2 nucleophilic, then you can get to answer choice A. Okay, now which is the strongest nucleophile in polar protic solvent? So in polar protic solvent, you have little positive charges that are trying to impede you. So the bigger space you have that your negative charge is spread out across, the better it's going to be because these are going to impede you less. So in this case, bigger is better. So the right answer should be answer choice A. If it was polar aprotic solvent, it's exactly the opposite. And fluorine would be the best because it'd be the smallest, so it could dart around and start attacking things really easily. It doesn't have any positive charges hindering it. Okay, now for question 13, which of the following would be the most reactive in an SN2 reaction? Well, SN2 reactions is the backside attack. It doesn't want to be hindered. So methyl is the best. We don't have any methyls here. There's no CH3Br. So then the next thing is primary, and then secondary, and then tertiary. So if you can just say primary, secondary, tertiary, this is an sp2 hybridized, so this won't do SN2 reactions at all. This is secondary. This is, again, sp2 hybridized, so it won't be an SN2 reaction at all. This is primary, and this is, again, sp2 hybridized. So if you just know that sp2 hybridized isn't going to react, you can narrow this down to B or D, and then from there, answer choice D is the correct answer because it's primary. Okay. The major product of the following reaction. So if I look at my nucleophile, it's I minus. And this is a secondary. So I'm going to go ahead and do my decision chart. So I have my nucleophile is a strong nucleophile, so it's going to favor 2. It's not going to go over to the 1 side. And then, if it's primary, it's going to favor SN2. If it's tertiary, it's going to favor E2. But in this case, it's secondary. So you can consider 2 things. Is it a bulky nucleophile? It's not. It's just an I minus. So it's not very bulky. It's narrow. So that also favors SN2. But if you're still not sure, this HI is considered a strong acid. So I minus is a weak base. So if you have a weak base with your primary, it's also going to favor SN2. So I'm going to say this secondary leaving group is going to favor SN2. So this is favoring SN2. Then your I minus is going to come in and attack and kick this out. So you have CH3 and hydrogen. This group doesn't change, but this one has inversion of stereochemistry. So the I comes in on the top and the hydrogen is now on the bottom. So the right answer choice for this one should be answer choice B. Okay. Oh, here, let me circle it down here as well. Okay, now we're on question 15. What would be the major product obtained when trans 1-bromo 3-methyl, so I'm going to draw 1-bromo to 3-methyl, and it's trans actually, so that should be a dash. 1-bromo 3-methyl cyclopentane is allowed to react with H2S at room temperature. Okay, so let's look at our decision tree. Is this strong or weak? Sorry, the nucleophile strong or weak? It's weak, it's neutral, so that's going to favor 1 reaction. So either SN1 or E1. It's at room temperature, and this is not a super bulky base or nucleophile, so I'm going to say this is probably going to be, and it's a pretty pretty narrow, so I'm going to say this is probably going to be SN1 over E1. But also, I'm just realizing none of the options, the answer choice has an elimination product. So that also tells you it's going to be SN1 over E1. So SN1 for inversion of stereochemistry means the leaving group's going to leave, and the attacking group, which will end up being SH, will form both a wedge and a dash. So you should get a racemic mixture where you have cis and trans with your SH and your CH3. So just looking at these, in this case, your SH and your bromine are both still there and your leaving group has to leave, so that's not right. And same thing with answer choice 4. Your bromine is still there, but your leaving group has to leave, so that's not right. So we're down to answer choices 1 and 2. CH3 and SH are on different carbons, and they're trans here, and they're cis here, so I think there'd be a racemic mixture of 1 and 2. Okay, and last but not least, which SN2 reaction would you expect to take place most rapidly? Concentration of the reactions, temperatures are all the same, so we know it's SN2. So SN2 takes best on a primary leaving group, but or methyl actually, and all these are methyl, so that's all the same. The next thing I'm going to look at is the leaving group, and chlorine is the worst leaving group, so I'm going to go ahead and nix that one out. So that makes me know it's A through D. Now, if we're looking at A through D, all these have the same substrate, the same leaving group. So the only thing left to look at is a nucleophile. Well, we know the negative charge is going to be better than the neutral. So we can go ahead and get rid of B, and we can get rid of D. So now we're down to just answer choices A and C. So that already gets you at a pretty good spot. You just have to decide which one of these is a better nucleophile. And we know that sulfur S- is a better nucleophilic attacking group than O-, so that's why we know that A is going to be the right answer. I hope this was helpful to you guys. I'll work out the free response questions in a separate video.